All right, so section 7.6. We're going to talk about moments. I'm going to abbreviate COM. COM means center of mass, just so we don't have to write it. COM and centroids. Yep. All right, so what we're going to talk about today is we could, if we wanted to be more detailed about it, we would call it a moment of mass. And mass, just to be complete, mass is the property of an object that resists motion, essentially. And a moment is, what we mean by a moment is that we are weighting something by its distance from an axis. That's what we mean by a moment. The way we're going to talk about it, I'll say from an axis. In statistics, often you talk about moments, and your statistical information is weighted by, for example, its distance from the mean. So you'll talk. They don't really call them moments in statistics, but moments are important because often you're talking about how far something away is from the mean. So we're going to talk about the moment of mass. So I'm going to say the moment of a mass m about a point is, and I'm just going to say the moment equals m times x. X is the distance from the point. So we're talking about a one-dimensional kind of thing. We have a mass on the x-axis. We multiply the mass times this distance from a particular point. We call x the moment arm, the length of the moment arm. And if we have a system of masses, so we have masses along an axis. So, for example, some kind of scale. You have your little sliding weights on the scale. That the moment about the origin for a one-dimensional system So the moment about the origin is m sub 0, and we just multiply each mass times its distance from the origin and add them together. However many we have. And our point masses, m1, m2, m sub n, are point masses, and they're located at the various x's. The center of mass and from here on out I'll abbreviate COM. We write as x bar is the moment divided by m, where m is the total mass. And the center of mass would be where that particular system would balance. So if if we thought of if we had these masses on a long rod, and they're located at some distance from the origin of the rod, if we put our balance point at the center of mass, then that system would be perfectly balanced. So for a discrete system, we just add the moments of each mass, and then to find the center of mass, we divide the moment by the total mass. So questions about the concept. Well, now that we're talking about adding things together, you might be able to predict where we're going with this. So we're going to, instead of talking about a discrete system, we're going to eventually we'll talk about a continuous system and how to find this. We'll talk about how we find the center of mass of a continuous system. Now, why would it be important to find a moment or the center of mass? One reason is, well, you can talk about where it balances. Another reason is if I took a handful of markers and I threw them across the room. Well, it turns out that we can analyze the motion of the system by analyzing the motion of the center of mass. So that the center of mass travels as if all the masses of these things were concentrated at that point, and that's the path that those markers would take. So we can think of the center of mass. We can analyze the motion of the center of mass instead of analyzing the motion of each individual piece. So that's one reason. Second semester, we'll go a little further with this. We'll get a little more sophisticated, and we'll be able to find other kinds of moments. So we can find the second moment of mass. So we multiply by the distance squared from an axis. That gives us the moment of inertia. And that has to do with how much an object resists rotation. We could talk about the moment of force, which is would give us the center of gravity. So if our gravitational force is not necessarily uniform, our center of mass and center of gravity might be different. We could have a moment of area. So multiply an area by its distance from something, and that might be useful for some things. So there's lots of kinds of moments that we could talk about. All right, so for a two-dimensional system, so we have some masses distributed in a plane. We define two moments. We're going to have one about the x-axis and one with respect to the x-axis and one with respect to the y-axis. So we're going to multiply the mass by its distance from the x-axis, and the masses by their distance from the y-axis, and we'll have our moments about the two axes. So let's see, we have masses m1, m2, m3, m sub n, located at these points, x1, y1, x2, y2, xn, yn. The moment about the y-axis. M sub y is each mass times its distance from the y-axis. M1, well, the distance of this first mass from the y-axis is x1 plus m2, x2 plus m sub n, x sub n. So notice that the moment about the y-axis has to do with the x distance, because the x tells us the distance from the y-axis. And the moment about the x-axis m sub x is m1 y1, because y is the distance from the x-axis, plus m2 y2 plus dot 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 m sub n y sub n. And the center of mass, x bar, y bar, is, well, the x coordinate of the center of mass is the moment about the y-axis divided by the total mass, and y bar is m sub x divided by the total mass. And the y bar has to do with the moment about the x-axis, because that's telling us that has to do with the y coordinates there.
Is that a y1?
Y bar, sorry.
Okay. I thought it was y.
I thought, I was thinking, I think I put a comma there by accident. So if we have point masses located in a plane, we can find the moments about the x and the y-axis, and then we find our center of mass, and that would be if we could imagine those points, the masses, say we have a thin piece of cardboard, so that's very light in relation to the other masses. We place these masses on this piece of cardboard at these various distances from the x and y-axis. If we put our pencil at the center of mass, that piece of cardboard with these masses distributed at those points would balance at the center of mass. And if you had something like that and you tossed it in the air, the system would move as if all the mass were concentrated at the center of mass. All right, so what we want to do, this is for a discrete system. What we want to do is now talk about a continuous system. So we have that piece of cardboard that I talked about. We want to find the center of mass of some shape of that piece of cardboard. So we call those planar lamina. And this addition then is going to become integration. Planar lamina, a lamina is just a thin sheet. So we're thinking of like I said, a thin piece of cardboard, a thin piece of wood, and we're going to have some particular shape. Well, that shape is going to have a center of mass. So if we put the shape on our tip of our pencil, it would balance somewhere. And that's what we're going to try to find. We're assuming a couple of things. One, the lamina is planar, and the density is constant. When we talk about multiple integration, second semester, we will talk about how we'll have a nicer way to deal with centers of mass, and our density does not necessarily have to be constant. But for what we're doing today, our density has to be constant. We're going to measure for planar lamina. Density is mass per unit area. So we're going to say this thing weighs well, I guess I'd be in the metric system, it would be kilograms per square centimeter or something like that. That's how we're going to measure our density. And we're going to use the symbol rho for density. It's like a curvy P. You just don't have the little top thing. But that's rho. All right, so what we're going to do is let's set this up. we have our lamina is going to be bounded by some curves, F and G. And we want to find the center of mass and our moments from x equals A to x equals B. The other assumption that we're density. The other assumption that we're making is we can consider the mass of a rectangle to be concentrated at the center. So what we're going to do is divide this planar lamina into little strips. Very similar to what we did with our work integrals. And I'm going to say that thickness of that strip is delta x. And I'm going to put, we're going to say this is located at x sub I. And I'm going to do the center of that at y sub I. So that's our setup. We have some planar lamina bounded by some curve, and we want to find the center of mass. Well, what we're going to do is divide it into these strips. We're assuming that we can treat the mass of that little strip as if it were concentrated at the center. And we're going to add up the mass of that little strip times its distance from the x-axis, the mass of that little strip times its distance from the y-axis to get our moments. Yeah?
Does it matter that it's not like a perfect rectangle? Not like the ends.
Here?
Yeah.
We're saying it's small enough, we can make that delta x small enough that it's essentially a rectangle. That's what we do in calculus. Calculus is integrating gives us a way to multiply by 0 and get something, and derivatives give us a way to divide by 0 and get an actual answer. So that's really the secret of calculus. We can multiply by 0 and get a number, divide by 0 and get a number. All right. So the mass of the lamina is the density times the area, because our density is mass per unit area. Well, we know how to find that, right? So the mass is the density. How do we find the area? Integral from A to B. How do we find the area between these two curves? Top minus bottom. F minus G. There's our mass. That will give us the mass of the region. So we in the end, when we find our center of mass, we need to divide by the total mass. All right. Let's find our moments. So this f of x minus g of x, that gives us the height of this rectangle, right? Can we agree on that? The dx gives us the width. So the distance from, I'm going to call this point here, I'm going to just put x sub I, y sub I. That's the center of that rectangle. How far is that rectangle from the x-axis? Y sub I. So that's going to give us our So that's part of what's going to give us our moment about the x-axis. Right? But how do we find y sub I in terms of these other quantities? What's the center of that rectangle?
You have to take another function that's
F of x plus g of x over 2, right? We're integrating with respect to x. We want the middle of that rectangle. Well, the middle, y sub I is going to be f of x plus g of x divided by 2, halfway between those two. So y sub I is going to be f of x sub I minus g of x sub I divided by 2. That's the distance of that object from the x-axis, or that center of that rectangle from the x-axis. We need to multiply that distance by the area and the density to get our moment about the x-axis. So our moment about the x-axis is rho times the integral from a to b, the distance from the x-axis, f of x minus g of x over 2, times the area of that rectangle. This should be plus, sorry. This should be plus. F of x minus g of x dx. So that's going to give us our moment about the x-axis. This gives us the coordinate, the location of the center of that rectangle. And our moment about the y-axis, well, how far is this, the center of this rectangle from the y-axis? X sub I, right? So that integral is a little easier. The moment about the y is the density times the distance from the y-axis, which is just x, times the area of that rectangle, f of x minus g of x dx. So that's going to be our moment about the y-axis. And then our center of mass, x bar, y bar, given by x bar is m sub y over the mass, and y bar is m sub x over the mass. So to find our centroid, or our center of mass, sorry, I'll talk about centroids in just a second. Center of mass, we have to do 3 integrals. We have to find the mass. We have to find m sub x. And to find m sub x, we have to do this piece that gets us to the middle of the rectangle there. So we integrate with respect to x. And we have to find m sub y. So what I do on a quiz or a test is I will say, set up but do not evaluate the integrals required to find the center of mass of this planar lamina. And then evaluate, and then find x bar. So you evaluate one of them. Or then find the moment about the x. So I'd ask you to evaluate one integral. And we will use, or the book sometimes uses the word centroid to refer to the center of mass. Usually, centroid refers to if we have something that's a uniform density, constant density. The centroid is, we think of the centroid as a property of the shape. So a triangle has a centroid, a rectangle has a centroid. We took advantage of that. The centroid of this rectangle is right here in the middle. Some other shape is going to have a centroid. Center of mass is a property of the material. So if our density is not constant, then the centroid can be different. The center of mass we think of as a property of the material in combination with the shape. So centroid we use to talk about a uniform density material. So if it's uniform density, the centroid and center of mass mean the same thing. All right, questions? All right, I want to look at a couple. Yes.
So for the density to stay the same, like that you could have different mass points. Does that mean that like if you increase the mass of a point, you have to increase the volume at that point too for it to like work with
This,
this?
well, in order to use this, we can't, the mass can't change at all. So this relies on the density being constant. So if the density wasn't constant, we couldn't do that. So during second semester, we'll talk about a way that we can handle varying densities. And we could think of maybe the density might vary, not because it gets thicker, but maybe the material changes. Yeah.
So what's the third integral you needed for the center of mass? So I understand that you need m, x, m, y, and then there's versus
Mass.
Oh, the mass one, okay.
Right.
And then how do you combine those? Do you just put them in that formula?
This, yeah. Mm-hmm.
When you're finding the center of mass, doesn't the density just cancel out?
Yes, when you do find the center of mass, you have the density in m sub y, and you have the density in m, so those go away. So the density ends up, it's usually we can just assume the density is 1 because it just multiplies, it's a multiplier and they cancel out at the end. All right. So let's look at an example. Often with these, the difficulty is setting them up. Very similar to what we did with work. So here is our planar lamina. This is y equals 2x. This point is 1, 2. So this is x equals 1. We want to find the center of mass, or the centroid. Now, before we do this, do we remember back in geometry where the centroid of the triangle is located? Well, you could, so the centroid is where some kind of line that has to do with the sides of the triangles meet.
Isn't it where you like draw the midpoint easier to draw line?
Right, so the centroid is from the medians. So we go from the midpoint of this segment to the opposite vertex. But do we remember where the centroid? There was a nice formula to talk, or a nice distance where the centroid was located. Do you remember? Well, let's do some calculus and we'll figure it out. All right. So this would be the way this would be set up is we could say it's a triangular region bounded by, if they didn't give you the picture, by y equals 0, y equals 2x, and x equals 1. So if they gave you a verbal description or written description, this is what the description would look like. It's describing that triangle. All right, so let's find our mass first. I'm going to say rho is 3 grams per square centimeter for this particular thing. So our mass is just going to be the integral of rho times going to integrate from 0 to 1. We're integrating with respect to x. F of x minus g of x. So it's just 2x dx. And when I evaluate this integral, I get 3 grams. So we get x squared 6x squared over 2 from 0 to 1, so we get 3 grams. The moment about the x-axis is 3 times the integral from 0 to 1. I said x, but I drew a y. Moment about the x-axis. This is where we had to find the middle of our rectangle. The y bar is at the middle of the rectangle. F of x plus g of x. So 2x plus 0 over 2 times f of x minus g of x times 2x dx. Easy integral to evaluate. And this comes out to be 2 gram centimeters. We have a mass times a distance. So my units are gram centimeters. M sub y is 3, integral from 0 to 1. Now we just have an x. F of x minus g of x, 2x minus 0 times 2x dx. That's the area if we think of dividing this into a little rectangle. If it helps you to draw the little rectangles, draw them in. There's the middle. And this comes out to be 2 gram centimeters. And x bar comma y bar is 2/3. And if we remember from geometry, the centroid in the triangle is located 2/3 of the distance from the midpoint of the side to the opposite vertex.
How'd you get 2/3 of
The m sub x divided by m,
Okay.
m sub y divided by m. I'll put, or sorry, this is m sub y divided by m sub x divided by m.
Well, don't you have 2/3 comma 2/3?
2/3, yeah, I just said they're both. So our coordinate, each of these equals 2/3. So our location is 2/3, 2/3. That's our center of mass, our centroid. And the centroid of a triangle is located 2/3 of the way across the triangle. To prove that analytically, to prove it geometrically, is a lot of work. I know because I had to do it this summer. It's a lot of work. To do it, we did it without coordinates also. It's called synthetic geometry. It was a lot of work. All right, questions? That's an easy example. Let's set one up a little different. We'll not evaluate all of this, but we'll set this up. Just so we are sure we know how to set it up. Find the centroid of the region. Bounded by y equals x squared and y equals x. And we're going to say our density rho equals 1. Well, let's draw a picture here. There's y equals x squared. There's y equals x. So we're talking about this little region. We want the center of mass of that little region. So if it helps you visualize, there's my little rectangle. What are these points? 0 and 1. So our intersection is at 0, 0. and 1, 1. Other types of regions, you might have to solve equations to figure out the points of intersection. And depending on the functions, that can be a tricky part of the problem, is finding those intersections. So we're going to integrate from 0 to 1. We could use horizontal strips. We can divide our region if it's easier. Divide it into horizontal strips. It'll work the same. We just have to adjust our integrals if we want to use horizontal strips. All right, so our mass integral is going to be our density, which is just 1, times the integral from 0 to 1, and it's f of x minus g of x. Be careful with, when you're doing this subtraction, that you subtract the smaller one from the bigger one, depending on your intersections. Make sure you're sure what the bigger function is. So this is going to be x minus x squared dx. So a nice easy integral to evaluate. Moment about the x-axis. It's going to be our density, integral from 0 to 1. Y is our distance from the x-axis. That's where we have to find the center of those rectangles. So we have f of x plus g of x, x plus x squared over 2. That's the location of the y coordinate of that little dot, times x minus x squared dx. So also, depending on your functions, this integral can be an interesting one to get to a place where you actually can evaluate it. So we end up having to multiply these polynomials. And m sub y is 1, integral from 0 to 1. Distance from the y-axis is just x, times the area of that little rectangle, x minus x squared dx. This one's not a bad one. When I evaluated this one, I got 1/6. When I evaluated this one, m sub x, I got 1/15. And when I evaluated for m sub y, I got 1/12. So my x bar is m sub y over the mass, which I get as 1/2, and y bar m sub x over the mass, which is 6/15 or 2/5. Does this make sense for this region? X is 1/2, so we're the middle, and y is 2/5. So if we got our y coordinate of our center of mass somewhere bigger than 1, we know we've made a mistake. If we got our x coordinate of our center of mass bigger than 1, we know we've made a mistake. So you can see if your work makes sense depending on your region. All right, questions there. If you have a nice simple plane region that you can divide into rectangles, you can find the center of mass without integrating. So if you have some kind of shape that you can just divide into rectangles, you can find the center of mass of each rectangle, which is just going to be the center of the rectangle, and just add to get your moment and your center of mass. So if you had a shape like this, you could divide it into rectangles. The center of mass of this one is going to be here. The center of mass of this one's going to be here. The center of mass of that one's going to be there. You assume that the mass is all concentrated at the center of mass, and you can find the moment and the center of mass of something like that without integrating. You could integrate, but you don't have to. All right, last thing for today, related to the center of mass. This is more for your information. but it's a nice thing to keep in the back of your head. The Theorem of Papas.
Sorry.
All right, the Theorem of Papas, I'm going to draw a picture here. So here's a shape. And I'm going to say this is a region R. I'm just drawing a rectangle here. And this is the centroid of the region. And we're going to rotate this region about some line. And R is the distance from the centroid of the region to the line. And what we're going to do is rotate this region about the line and generate a solid of revolution. So for this particular one, I'm just going to draw another picture here. There's L. We would get something like this, and there's my region, like so. And we're rotating that about L. So there's my solid. The volume of this solid, so this is R. V equals 2 pi r A, where A is the area of the region. So if we have a region where it's easy to find the centroid, a rectangle, a circle, I don't know, an ellipse, and we rotate that about some axis, the volume of the solid that we generate is 2 pi r A, where r is a distance from the centroid to our axis. And you can prove this by finding the volume in other ways that we already know how, and finding the centroid and showing that those two quantities are the same. So if you have a nice, easy region, a region where it's easy to find the centroid, we can find a volume of revolution very easily using the Theorem of Papas. Yeah. All right, questions? Okay. Next time we'll talk about fluid force. There we go. Whoops.